So today we are going to start a topic called optical instrument, and this topic is previously was part of only JEE-Mains, but now this is also part of JEE Advanced. So the weightage is certainly has increased. So we can expect some question from this chapter or this topic as well. So this is a extension of the chapter called ray optics, and the ideas of lens will be used here to demonstrate that how various optical instrument works. So in our syllabus, we have 3 or 4 different types of optical instrument that we are going to study. So before we start this topic, we need to understand certain thing about the human eye. In context of physics only. So I'm not going to teach you biology, definitely. The simple reason is I don't know biology. So this is the simplistic diagram of human eye. So first of all, we need to understand what is the meaning of size of the object, how human eye perceive or human mind perceive the size of an object. So size of an object having two meaning. One is called the linear dimension. So size of object. In case of lens, what you studied so far, when we say size of object, we talk about the linear size of the object, or we can say linear dimension. But there is another size of the object which we perceive. And when it comes to the perception of the size of the object, what we really care about is called the angular size, or you can say angular dimension. So first of all, we need to understand that as a brain, our brain is not able to understand what is the actual size, because the same object, if you look from the different distance, you can clearly see from your own experience that the size varies. So even the moon appears as a small disk. It is not because it's a small, it's because what we really perceive is the angular dimension. We never perceive the linear dimension. So first thing we need to understand is that, okay, the size as perceived by the human brain or human eye is the angular dimension. So if I draw something like a hypothetical an object, and if I join this object to the human eye, and if I extend this line, highly exaggerated diagram, then this angle we call the size of the object. Which size? Of course, we say angular size. And this HO we can call the linear size. Okay. So for human eye, it is always the angular size which matters, not the linear size. And we are not concerned about the linear size. Now, what happens that if the object will start approaching the human eye, from the common experience, we can say, what will be the effect on the angular dimension? So as the object will come closer, what will happen? The angular size will increase or decrease or remain same?
Increase.
So it is going to increase, right?
Yes, sir.
Yes.
What happens to the linear dimension? It is unaffected. So linear dimension is the reality. I mean, that reality is there, but we are not concerned about the linear dimension. What we are concerned about is the angular dimension. So the obvious thing is like technically, if you talk about as the object will approach the human eye, the size will keep on increasing. So when we can see the maximum size? When the object is closest to the eye, correct? So technically or theoretically, we can say that the size is maximum when it's really bad, but anyway. But the problem is, as you come closer to the eye, the size will increase in terms of the angular size, but the image becomes blur. In a way, you can say that the human eye is not able to focus the image on the retina, because if we take the entry of the human eye as the human lens, generally the eye lens is slightly ahead from the human sclera, you can say. Just a moment. So we have eye lens, a jelly-like structure, and this eye lens is attached to the some muscle called ciliary muscles. And what is the role of ciliary muscles? The role is to change the shape of the human eye lens. Okay. So it can stretch it, it can compress it. In the relaxed position, when the lens is not stretched, in the relaxed position, the focal length is minimum, you can say maximum. But when objects come closer, then you need to decrease the focal length to form the image on the retina. Why we need to decrease? Because the distance of the lens with the retina is fixed. In a way, you can say that the screen and the lens is fixed. So we have a fixed lens. We have a fixed lens, and also we have the fixed position of screen. So we have no choice to alter the separation between the lens and the screen. This is roughly size of the eyeball, which is roughly 2.5 centimeter. So this part I cannot change. So our screen is fixed. This is the retina. So you can imagine retina as a screen and the lens as the, of course, the optical instrument. And whatever light is coming has to form its image on the retina to make it perceptible to the human brain. Okay. So as the object distance from the lens will change, the f must change because v is constant. So if you know the basic lens formula, which is 1 by v minus 1 by u equals to 1 by f, what we cannot change is v. So for every u, you must change the f. And therefore, this variation of f is a physical constraint. It means our brain, or you can say, sorry, human eye, is able to change up to certain extent, but it cannot attain any value it wants. So this constraint leads to something called power of accommodation. So the power of accommodation says that for every u, the f must vary to form the final image on the retina. If you fail to do so, then the image will be blurred and basically you won't be able to see it clearly. So coming closer to the eye is, of course, will increase the size, but that size is of meaningless. I mean, the size is of no meaning because although it's big, but it's blur. So what we want is, we want that the image, final image should be on the retina and the object should be clearly visible to the brain. Okay. So why I'm using the word brain again, because we don't see through the eye. Eye is just a medium to which allows the light to enter, but the vision is developed as a perception in the brain only. And the light which you receive here, okay, in this part, that light is incident on something called the rods and cones, which are cells inside the eye. So rods and cones are two separate kind of cell, and the rod is able to understand or explain to the brain what is the intensity of image. It means how brighter the image is. And cones are responsible for the color of the object. The color of the object is again function of frequency of light. So color is of course not the function of wavelength, it is only function of frequency. It means how many wave you receive per second. That is the whole idea of the color of the object. Now this idea of color comes because we have cones. Many animals do not possess this cone cell, and therefore for them the world is still gray. Okay, they don't see the color. There are creatures who are having maybe more sense of color. So we human, I mean being, are able to only see a, you can say, a finite spectrum of electromagnetic radiation. So we are only able to see the finite spectrum of EM radiation, and that finite spectrum we call visible spectrum, and be precisely defined from violet to red. We call VIBGYOR. Or to make it interesting, I can write like this: V I. So you can, okay, you can argue that, okay, how we are only able to see 7 different component of color. In fact, the VIB is not distinguished, rather they are only one. So it is said that indigo and blue is not distinguishable. So technically we only see 6 colors. We don't see 7 different component. So we're not able to distinguish the indigo and blue. It is quite closer. The frequency more than violet we call the UV, and the frequency less than red is called infrared. So beyond the dimension of visible spectrum, we have ultraviolet spectrum, we have infrared spectrum. And in the spectrum chart, you can see we have some other spectrum defined like X-rays, gamma rays, cosmic ray. Okay. So all these things are there. Now you may ask that why we are only able to see this many colors, because this is the physical dimension of the cones. So basically the gap between, you can say, two cones in a nano scale defines that which kind of wavelength can be intercepted and which kind of wavelength cannot be intercepted. So you can say that if a wavelength is very, very small, it can pass through this. In a way, it will just pass like an X-ray passing through the body. And in a way, because of the small dimension, the brain will not be able to perceive it or intercept it. Similarly, if you go beyond red, the issue is you are the same wavelength is touching so many cones that the interception is again blurred in a way. So it is the physical size of the cones which decides that which part of spectrum we are able to see and which part of spectrum we cannot see. And because by the nature of human evolution, the God has given certain dimension which is predefined, and therefore we are only able to see these many, uh, you can say, component of light. Now with a special technology, we can define a different kind of retina called the digital retina, and probably by designing some small scale integration chip, we can intercept even the UV rays. We can intercept even something beyond this also. It is all about the size. What we need to understand is it is all about the size. Anyway, that is not our discussion. That is not our, interest. So the cones are responsible for the color which you see. The rods are for the intensity of image, and this optical nerve which enters the brain. Of course, nervous system eventually. These are the carriers of the electromagnetic signal, and I have discussed many times that light is nothing but an electromagnetic radiation in which we have the oscillating electric field and we have the oscillating magnetic field, and these are oscillating in two mutually perpendicular planes. These are oscillating in the two mutually perpendicular planes, and they have the frequency of oscillation, which is just simply the sinusoidal curve. And we know that every sinusoidal curve we can express something like x equals to a sine omega t. In this case, it is sine omega t is good enough. And the x can represent any physical quantity. The a can represent any physical quantity. It need not to be just displacement only. So x can be the electric field. Then this is E naught sine omega t. And because it's a progressive wave, so those who have studied the wave, they know that every transverse, progressive wave we can represent like this: omega t minus kx. So omega is the frequency part which we need to understand. This is the frequency part. The k is something to do with the medium, right? So if you remember that the k represents the medium property indirectly. So the electric field is E naught, which is the amplitude of oscillation, which is like the highest value that E can have. And similarly, the x can be replaced by the b value called the magnetic field intensity or magnetic field induction of intensity. And these are basically progressive, the way which propagates. Okay. So in case of electromagnetic wave, the term omega and the term speed of light and k can be related. Omega equals to kc, or you can say k is nothing but omega upon c. If you change the medium, the k will change because the c will be replaced by some speed of light v, and therefore the representation will change. Now, why this is important? Because when you solve the question of EM wave, then you need to know how to read these terms carefully. And by reading the k values, you can actually determine the refractive index of the medium. So, for example, right now, if I have written, if I write the equation like E equals to E naught sine omega t, and k we can write as omega x by c. So I can take common as omega t minus x by c. The c is representing the speed of light, and therefore this equation is representing the electric field in vacuum, isn't it? But imagine if I write the same equation in this fashion. So let's say if I'm writing the question as omega t minus x by, like this, 2x by c, which we can rewrite as E naught sine omega t minus x by c by 2. And given this equation, can you read the refractive index of a medium? So what mu it is representing? So we know by definition the mu is defined as c by v. And because c is c, but if you look at the equation, you can easily understand what is v here. The v is c by 2, because we have to compare the x by something value, and this value represents the velocity of light. So definitely this equation is representing the propagation of light in medium other than vacuum, and therefore you can see the mu turns out to be how much? 2. Similarly, if I write E equals to E naught sine omega t minus x by 3c by 4, let's make it 3c by 4. What will be the refractive index here? So the mu turns out to be c by v, and the v we can write as 3c by 4, and the answer is, and this is very much known to you, this is the refractive index of water. If you have solved question of ray optics in the past, you might be knowing this. So first thing you need to know is how to read these equations anyway. So that will be part of a chapter called EM wave. It's good to know it. So why I'm emphasizing on E? Because the brain only understands the electrical signal. So the way we perceive object is through the electrical signal, and when these signals arrives at the retina, it is carried by the optic nerve to the brain, and a particular part of the brain is able to decode that as an image. So everything which you have seen before is in a way stored in the brain somewhere, and when you see that object again, it is like a matching the pattern, and because the image file is stored in the brain is able to search for that image file, and okay, it will help you in telling that okay, this is the object called maybe a pen or a textbook, paper, or whatever you have seen so far in your life. So the brain only understands the light concept. The brain understands only the field concept. Okay, brain has nothing to do with the object. And therefore, it is important to understand that, okay, when we perceive something, how we exactly perceive. Now, coming back to the human eye that we were talking about. We want to see the object, and we want to see as big as possible. But we don't want to see it blurred. We want to see it clear. And therefore, you cannot keep on bringing the object closer to the eye, because if you keep on doing so, eventually it will become blur. So what we do is, we have defined one standard value beyond which everything is assumed to be blurred for the normal human eye. And this standard distance is called capital D. And this is taken as a value 25 centimeter. So the capital D is called the distance of, or you can say least distance of, to be precise, least distance of distinct vision. So this is the minimum separation at which, of course, for healthy human eye, so this minimum distance at which we can see the clear as well as biggest angular size of the object is actually called the size of the object. So this angle we represent by theta naught, and therefore the angular size of any object, and this is the unaided eye. What we call this as unaided. We have not used any aid. So when you bring something between the object and the human eye, we call it aided eye. Like you bring some convex lens, you bring some concave lens. So then the moment you bring something in between, it becomes the aided eye, but we are talking about the unaided eye. So what is the biggest size of the object that we can see without using any aid? So that is called the size of object in the context of optical instruments. The size of object is well defined in terms of h naught upon d, and this is a fixed definition. I mean, we are not supposed to change it. So the theta naught for unaided eye, and of course we are talking about the objects which are at finite separation from us. So in our day-to-day life, what we see is objects at finite separation. This definition will change once we start observing the cosmic bodies or celestial bodies. So when you're looking at moon or sun, of course, you cannot bring sun at 25 centimeter and see it. You know what will happen. So the definition will change, of course, there. So I'll tell you how to define the size of the sun there. But right now we're talking about the finite side object which are at finite separation. And for those objects, the size we define in terms of least distance of distinct vision. And the way of writing is pretty much standard. It is the de facto of writing. And we have to just follow it. Now, why D? Because if you come closer to the D, the image becomes blur, and we want clear and magnified image. So we really want as big as possible, but at the same time, we want that, okay, it should not give you the blurredness. So this is the first thing that we need to know in studying the optical instrument. What is the angular size? Clearly, you can see it is depending on the linear size and the least distance of distinct vision. It is in short, we can call it LDDV. Okay. Now the question is how to magnify the image, how to see it bigger without coming closer. And that is a problem. At the same time, there are two things you are trying to achieve. First, you do not want the object to be closer than D, but you want theta to be more than theta naught. So that is certainly not possible without aid. We need some aid to achieve that task. And that's come the concept of magnification or the magnifying power of the optical instrument. So basically these optical instruments are called aid. And all the chapter, what we are going to study here is the called aid only. So whether we are using the microscope or compound microscope or telescope or terrestrial or Galilean or whatever, all are called the aid. They help in achieving the bigger theta without compromising the goal that it is closer than the D. I mean, they are away from the D for sure, but at the same time, they are still able to create bigger theta because the brain, the human eye can see clearly only when it is more than D. If it is less than D, we cannot see. So the goal is to increase theta without making it blur. It means we want our image such that it's obtained bigger angle than theta naught, and it is still away from the D value. I hope this part is clear what I'm saying. What we want, what is our goal? Our goal is to create the angle more than theta naught. And also, whatever we are trying to create should not bring the our image, or you can say object, less than D value. So we want always more than D and or equals to D, you can say in the worst case scenario, D or more than D, and theta is still bigger. Okay. Now the eye with some defects of vision, what happens? They have a different D. Also D varies with age. So a younger kid will have D as small as 7 centimeter. With old age, it goes to 200 centimeter, that is roughly 2 meter. Now 25 is taken as the standard, and who has taken this decision, I have no clue about it. but someone has taken the decision. So if your goal is clear, then probably we can proceed to different types of optical instrument. What is our goal? Our goal is to increase the angle. Which angle? The angle that the object is subtending on the retina. But if the object will subtend more than theta naught, it has to be closer to the eye than the D value, which is going to make it blur. So the goal is not to bring closer, is still getting bigger, bigger angle. So we are going to see how we are going to achieve it. So we have something called magnification. And because we are talking about the magnification in context of human eye, so there is a name, angular magnification. So far, what you study in ray optics is called linear magnification, in which we see or we take the actual size. But what really matter for us is the angular magnification. The linear is for writing purpose. When it comes to perception, it is only angular. And this was the question also in the JEE-Mains, one of the JEE-Mains, in which they asked that what is the meaning of angular magnification. It was purely theoretical question. So the angular magnification, I can add m theta, is defined as the angle subtended by the image, angle subtended by the image upon. Now this is interesting. Upon, what I'm going to write is very standard. Again, it's a standard that we defined earlier. Angle subtended by the object kept at LDDV without any aid. So this, the denominator is very much standard. We cannot change it. The numerator will, depending on the situation. So in the series of optical instrument, the first optical instrument is called magnifying glass. And we call it simple microscope. Simple microscope. So we all know that the very famous convex lens act as simple microscope, isn't it? So for that, you need to remember the ray diagram of the simple microscope, or don't call it a name, just tell it a convex lens. So when it comes to the ray diagram, we have certain things which we need to remember, that for a lens, and of course we're talking about the thin lens, we have optical center, which is the center of the aperture through which the light will refract. We have primary and secondary foci, and depending on the ray direction, one of them will be principal primary focus and another will be principal secondary focus. So the primary focus we write by F and the secondary we write by F dash. And then we have, okay, 2F. 2F is the distance at which if you keep the object, the image will form at 2F on the other side. Now, if you know the types of image formed by the convex lens, you remember that it will form the real image when the object is beyond F or F. So real image will form only when you are away from F or you are at least at F. At F, what will happen? If the object is at F, what happens? The light will travel, and after passing through the lens, it will become parallel to the principal axis, and therefore where the image will form? at infinity. So we say that image is going to be formed at infinity. Is this clear?
Yes, sir.
And what is F meaning? If the light is coming parallel to the principal axis, if light is coming parallel to the principal axis, then after refraction it will pass through the F. So they exhibit the reverse character, and that is also the property of light. So the light coming from infinity will pass through F. So whatever starts or begins from F will go to infinity. That is the principle of reversibility of light, which we should be aware of. Now, the real image is only formed when the object is anywhere, either at F away, F means F distance away, or at F or F more than F. So if you are beyond left of F dash, you're going to get the real image. And if you remember the idea of real image can be magnifying or magnified as well as diminished. So when the real image is magnified, anyone? The real is magnified only when the object is where to where?
F to 2F.
F to 2F. So only when the object is between F to 2F we have magnified. And of course we are looking for magnification. So it's meaningless to go beyond 2F, right? At 2F we have same size. 2F and F, if you are somewhere between, you are bigger than the object. And that is the first goal. Okay, we want bigger value. But there is a problem. If the object is at F and 2F, between F and 2F, our goal is not the magnification of object. Our goal is increase in the size of the object. Which size? Angular size. So imagine a situation where we believe that my object is somewhere here. You can see this angle is still very small. In fact, if the focal length turns out to be more than D, let's say the focal length itself is D, keeping something here will be going to subtend less angle than the object. So are we really achieving the magnification? See, we are achieving magnification in context of linear dimension. In context of angular dimension, are we achieving magnification? The
No.
answer is no. So magnification in the linear dimension is not the criteria to call magnification for the brain. Our idea of magnification is angle, not the size increment. Okay, that is the problem. So what we do exactly? We look for the other property of convex lens. We know that convex lens also forms the magnified image if it is virtual, if it is between F and the optical center. So when the object comes closer to the F, because see, we want bigger angle, and for bigger angle, we should bring the object as close to the optical center as possible. Okay. So now to increase the angle, I have to make it bigger, and if you bring it closer, it will be bigger. And the property of the convex lens is that when the object is between optical center and the F, it again forms a magnified but virtual image. I hope you remember this magnified and virtual image. Everyone?
Yes, sir.
Yes.
So then I can proceed. If you don't know, I will explain. In case if you know, then I can proceed. So how this magnification of the simple microscope is achieved? We'll try to answer again. This is our lens, a simple convex lens, principal axis, optical center, F dash, 2F dash, F, 2F, and here is my object. So this is, hopefully I will be able to do that. So the light ray which will move parallel to the principal axis will pass through. Okay, we know all this. So it will pass through the focus. And the other light ray which will pass through the optical center will pass undeviated. And you can clearly see, are these two rays going to meet in this side? In the direction of proportion, are they going to meet?
No.
It means they will never intersect really. So there is no question of real image. Real image means the real intersection of light rays. So when they fail to intersect in the direction of proportion, what we do? We proceed it backward. So we look for the virtual intersection or a hypothetical intersection. So you extend the light ray in the backward direction because you fail to get any intersection on the forward direction. So the only choice is okay. Looks like my job is increased now. Okay, hopefully I will be able to. This can. Okay, finally, some manipulation, and now you can see that is now they are meeting while producing backward, and every extension of the light ray in the direction in which they are not actually moving, we show it by the dashed line. And why we do so? Because the human eye is somewhere here, right? This is the human eye. Where is the human eye? Which color of human eye is nice? Okay, this is fine. So human eye, what do we see? Do we see object? Do we see light?
Right.
Do we see object? Do we see object? Do we see light? So what do we see?
Light.
Only light. What we perceive?
Object.
Object. So vision is perception. This is perception. This is vision. The concept of ray optics is explained in terms of vision, not in terms of perception. And therefore, the way you receive the light is the end way or end goal of understanding how the object should be. So this human eye, if we'll trace these two light ray backward, it will clearly see the object to be here. And we can draw something like this. The question is, this human eye is perceiving what? The actual object or this virtual object?
Virtual.
So the red line is something what we are perceiving, isn't it?
Yes.
So human eye is not aware that, okay, this light ray is coming from this object. No, it's not aware. And you can clearly see that you always wanted to increase the angle. No? So what do you expect? This distance should be less than d or more than d. How to achieve magnification? The distance from the optical center to the actual object should be less than d or more than d,
Responding.
which also gives you the idea that the focal length of the lens must be more than. Do you realize this? So
Yes.
for magnification, the first thing is we must have the focal length more than d. So we need magnification, and that is only achievable when we have the condition that f is more than d. If it is less than d, the theta will never grow than the actual value. Now, the human eye is not looking at this object, although the object is quite closer to the lens. Okay, this is of course not d. This is let me remove this. This I should not have written here. That was the idea. Okay, so the f must be more than d. So this distance from the object to the optical center, what we call u. That is the definition, right? The distance
Yes.
of object from the lens we call u. Now, one thing is clear that our answer, the u should be also less than d, isn't it? Or you can say the value of the u must be less than d. We are trying to achieve magnification, and therefore earlier it was kept at d. Now it should be kept less than d. Then only we can achieve the magnification, because our magnification actually means the angular magnification. We want bigger angle than before. And because the human eye is looking at this object, and this object is quite far from the d, isn't it? You can see this distance is quite away from d. Therefore, this can be clearly seen. The brain will be able to perceive it distinctly because it is at a far separation. At the same time, it is separating angle which is bigger than theta naught. So by that definition, what is the magnification? What is the angular magnification? What we can write here? The answer is theta upon theta naught. Now this theta is not for the object. This theta is for the image actually. Luckily, this theta appears for the object as well. Because of the diagram, you can see the similar triangle. This theta is not for h naught, rather it is for hi. But because of the construction, you can see this theta can be derived using the HO itself, which is blessing in disguise. We never thought about it. I was looking for the image and the angle subtended by the image. Fortunately, I would say that the theta I can derive in terms of h naught and u. That is a fortunate event. So what we can write theta? We can write theta as, you can, for a small angle, we know what to do. We can write theta as tan theta, right? And what is the tan theta in this similar triangle?
Not by
H naught by u.
you.
And theta naught is not defined here. Theta naught is defined earlier. That is the unaided I, predefined. H naught by,
D.
that is predefined. I mean, this is what is already in place. I cannot change it. And therefore, the angular magnification that we achieved is how much? What is fascinating here, that this has nothing to do with the actual size of object. Okay. Human eye will see something magnified or diminished based on the position only. It is a d by u. And this is the formula. This formula is the end of the simple microscope. D by u is the formula we have to go with. Now the question is, we have to go for two different things. So we have something called types of vision. And why we talk about the types of vision? That there are two types of vision. One is a relaxed view. Okay, relaxed view means the eye lens is relaxed position. The ciliary muscles are relaxed. So the first is called normal vision. And what happens in the case of normal vision? Human eye is in relaxed position, And when we are in the relaxed position, I mean, we means, I mean, the human lens, when it is in the relaxed position, when you look at very, very distant object, the only time when you're stressed, the eye is stressed when you're looking at objects which are very close to you. And why it is stressed? Because when the light, when the objects are very close to the human eye, what happens? If you are close to the eye, the light will travel as a diverging. So from the nearby object, the light will be always diverging. And therefore, to focus on the retina, you have to bend a lot. You can see, can you see the amount of deviation suffered by the light ray? But imagine a situation when the object is at infinity, which we call the distant object, distant. You're looking at the stars, moons, okay. How the light ray is coming? Roughly parallel to the principal axis, isn't it? And now when this light ray will bend and reach the retina, you can clearly see the deviation is, or deviation required is lesser, right? So in which case the eye lens has to bend more when the image is, or when the object is kept at infinity, or when the object is kept in close by, nearby.
Nearby position.
Close.
So in that case, you have to change your focal length a lot to achieve the task of forming the image on the retina, because as I said, the screen is constant. We cannot change the position of image. Our image must be on the retina. So the only thing you can change is the focal length of the eye. And here we need to, in a way, decrease the focal length. So when you try to decrease the focal length to form the image on the retina, it's a very stress condition. So we have a strain. Certainly we have the strain in the human, I mean, eye lens. Looking at the distant object is a feel good factor. That's why when you go to beaches or mountain, or if you gaze the night sky, your brain naturally feel calmer. Because when you're looking at those, when you're going to those places, what you're looking at is the very distant object. And that brings the sudden calmness. And therefore it is said that okay, we should go for a visit. We should, I mean, go to some beaches or mountains. There is a scientific reason. You go there, there are 3-4 things which actually happens. One is the molecules which they release. The nature releases certain molecule, and it will activate certain hormone which give you the feel good factor. Okay, so definitely we have the feel good factor syndrome. Dopamine is the hormone which gives us the feel good factor. But scientifically also, going to these places will give you the relaxation in terms of looking at the object. So your eye is really relaxed. It is unstressed. The lens is unstressed, and therefore you will feel sudden calmness. So of course there is a scientific reason also why we should go to such places. If you are living in a small room, of course you need some big space. We put some mirrors. So if you go to mall, they put life-size mirror. And why they put the life-size mirror? Because when you are looking at the plane mirror, which are big size, they replicate the same image at the same depth. So when you look at yourself, you see yourself at a distance, and so you get much relaxed. Anyway, so we have some other reason also. The other distance, the other type of vision is called LDDV, the least distance of distinct vision. So what LDDV does, it gives you the best possible magnification under the stress condition. So human eyes is trained. Okay. And definitely what will happen with age, this part will be difficult. I mean, with age, what happens? We are not able to adjust the eye lens focal length much because we have a limitation. The weakening of ciliary muscles over the age takes away this ability to accommodate, and that lead to something called the presbyopia or hypermetropia. So with age, we don't see the nearby object. The farther objects are easy to see because we need to bend light by less value. But to see the nearby object, we need to bend more. And therefore, in old age, generally we aid the eye with a converging system which can bend something for me so that the bending job of actual eye is less than before. So you know that in old age, generally we use, generally I'm saying, we use convex lens. We need some converging system. At a young age, what happens? Your eye power is, I mean, your eye is so powerful, its bending ability is so high that we need to aid the diverging system so that we can see the distant object, because your eye is so powerful that it will be able to bend the light much before the retina, which is not good. We want the bending to be here, not here. So we aid the eye with some diverging system, which we call concave lens, which will deviate a bit, and then this will again finally after convergence it will come to here. So we have the myopia at a young age and hypermetropia at old age in general. Okay. The other things are also there. So we need to understand the normal vision and the least distance of distinct vision. In normal vision, what we want to achieve is the final image should be at what we want, final image at infinity. But in the LDDB, what we want? Final image at where? D. We want the final image at D, and this will lead to the maximum possible magnification. This will be less than maximum. This will give you magnification, but less than the upper limit. I hope this is clear, guys.
Yes, sir.
Sir.
So now the next part is simple, common sense. So for normal vision, now that comes back to the concept of lens. For what value of u, the image will be at infinity? We all know. For what value of u, the image will be at infinity? Tell me, guys.
F.
F. So for normal vision, the magnification will be d by u, but we know that u must be f, and we're done. Over and out. And for LDDV, we want V to be at D. So in a way, we have to use the lens formula. Because so what is the V value? We want V to be at minus D. Let's call U as minus U because this is a symbol, this is a value. And F is plus. So what you can see that 1 by U turns out to be 1 by F plus 1 by D. Correct? But the angular magnification is defined as D by U. So D into 1 by U, which you can write as 1 by F plus 1 by D. And therefore you can see the angular magnification is defined as 1 plus D by F. This is the way of writing. So you can see that d by f will give you some answer, but definitely it will be one more, d by f plus 1. Okay. And if you look carefully, we have discussed. Oh, I made a mistake here. The f is less than d. No? So the d by f will give you the magnification plus 1 extra. Now you can think that what is this called? In terms of camera, we call this as optical zoom. And how we express? By some number 2x, 3x, which means how many times. So x 4 times. So you can see that if the optical zoom, if the d by f turns out to be, let's say 2 here, let's say if I choose f as d by 2, then m theta will be 2. But in this case, the m theta turns out to be 3. Now it is a huge difference. 2 times to 3 times is a huge difference. Although it looks like just 1, but you are making a 1 kilometer size object into 3 kilometer size object, which is really huge. So every camera comes with optical zoom, and the mobile phone cameras are nowadays very much capable to achieve up to 3 to 4 optical zoom, which gives you the picture quality without blurring the image. Beyond that, we have also artificial zoom called the digital zoom, that it will spread the pixels and will make the image blur. So if you want to go for a camera, and if it is written that it is having the let's say expensive camera, and the optical zoom achieved is 10x and the digital zoom is 20x, you should go for the 10x. Someone with a bigger optical zoom. So let's say if I have 5x and 20x, 5x optical, 20x digital, or 10x optical and 15 digital, I'll still go for the 10x. Now the digital zoom is generally used for the forensic purpose. Let's say I want to investigate some crime, and in the CCTV camera, I can see some image which is not clear. So generally we increase the pixel size. We try to zoom it and try to identify the criminals. Anyway, this is your simple microscope with two simple formula. For normal vision, it is d by f, which is logical because we want the answer to be at infinity. So I didn't use the length formula because we know the answer directly. But for the least distance of distinct vision, we have to use the formula properly to achieve the answer. It's good to remember this answer. This is so famous that one should remember the answer. Now, if they mention the u value, then you have to simply use the d by u formula to get the actual answer. Let's say they give you u value, that object is kept there. You can get the answer. So after the simple microscope, which is having the very limited optical zoom, roughly it is said that it can go up to 10x zoom maximum. And that is not sufficient for a variety of purpose. So we really want some more magnification because we are ambitious. We want more and more magnification to see things better. And thus we design something called compound microscope. As the name suggests, compound means we need to use more than one lens. So when you use more than one lens, there are some technical terms that we need to understand. So let's say we have lens number 1. We have lens number 2. On one side of the lens, we have the object kept. So if you think of some, let's say, microorganism put on the slides, and if you put that into the beneath the lens, the object is kept on a side and the lens facing the object is called objective. Of course, in between you don't do anything, and then the human eye is on this side. So the lens which faces the human eye is called eyepiece. So the first thing that you need to know is the definition of objective and eyepiece. What is objective? The lens facing the object. That's a very logical definition. Then eyepiece is the lens facing the human eye. Okay. So what do you want? Again, you want the magnification. So we define the focal length of objective as FO and the focal length of eyepiece as FE. And the general purpose of compound microscope is to see the very tiny objects kept at finite separation. So when you add two lenses in this fashion to see the object at finite separation, it is called compound microscope. But if you use a similar lens combination to look at the distant object, the celestial bodies, the name will change to astronomical telescope. Combination is same, like things are almost similar. Certain diagram will change. So the compound microscope we study in context of object at finite separation from the objective. Okay. So what do you want? Of course, you want that the object from the objective after passing through the objective should go to the eyepiece. Okay. Because if it will not go to eyepiece, we won't be able to see it. So we want real image because we want the image on the right of the lens. So for every object, when you get the real image, when the object distance is how much? So how far
Greater
the
than-
object should be kept from the objective? More than F.
More than.
So we call this as U naught, and technically U naught should be more than equals to F. Okay. Now by using the definition of magnification to achieve the maximum linear magnification, generally the purpose of the objective is to achieve the maximum linear magnification. Okay, so we have a really tiny object and we want the maximum linear magnification. So what is the magnification formula for the lens? The linear M equals to V by U. It's a direct relation. And this you can write as 1 by V minus 1 by U equals to 1 by F. And if I multiply with U, U by V is minus 1, U by F. So V by U is how much? We know F is positive, U is negative. So if you want to put into value, you can write as F upon F minus mod of U, the distance value. Now tell me guys, when the M will be maximum? When U is equal to F, right?
Yes.
In that case, it is going to be maximum. But we
Yeah.
want the real image to be formed on the right side on the principal axis. So for that, we want to answer not at infinity, but less than infinity for sure. So the U we want as close to as F, but not F. And also we want U to be more than F, isn't it? We want U to be more than F. Why more than F? Because we want real image.
Real image.
So our goal is to achieve the real image. Our goal is to achieve the real image. Our goal is to achieve the highly magnified image. So what we are doing is by adding two lenses, of course, the eyepiece will be similar to the microscope, simple microscope. The purpose of objective is to increase the linear magnification at first go. So the constraints are very much obvious. The U naught should be more than on a side which is bigger than f, but it is close to f. So we write as more than close to f. Technically, this is the condition. And then what you want next? So I'll make it a bigger size. The light ray will go. So we want some bigger image. And this diagram is apt diagram, you can see clearly. And we also want the real, so now you can see it's real. Now this image, this is the actual H naught. This is the H, the intermediate image, the first image by the first lens. But the image of the first lens will act as object for the second, isn't it? I'll make it slightly. I know what will happen. Now, what is the angular size of this object for the eyepiece? To know the angular size, we need to draw a line from tip of the object to the optical center of this, isn't it?
Yes.
Because what we want is the angular size. And when it comes to the eyepiece, we always look for the theta. Okay. So this is the theta part. First part is done. The next part is what to do is we extend this line in the backward direction like this. Okay, we'll just expand. Why? Because we know that we are going to get the virtual image as a magnified image. So our next goal is to achieve the virtual image. So what is the condition for virtual image? The position of the first object, first image must be within the
Photo.
focal length of eyepiece, isn't it? I mean, somehow this should occur. I don't know how, but somehow. And the distance of the first image from the optical center of the objective So our goal is to achieve the virtual image, and therefore the first image of the objective must be within the focal length of, or must be within the focus of the eyepiece. And that's why you can see I have written something FE dash. Okay. Now the distance of a first image from the objective we write as VO. And the distance of the first image from the eyepiece we can write as UE. So I hope the terminologies are clear. The U naught, V naught, UE.
Yes.
Everything is clear. Okay. So what we want is this. How to complete the diagram, because we have left the diagram. We need to complete, extend further. Okay. Then so you can clearly see I need to extend this lens bigger. Yeah, that's better. And after that, what will happen? These light ray will, the yellow line will eventually bend towards the normal, towards the principal axis basically. So the way of drawing is, okay, I'll do some trick. So this is my image. I'll draw somewhere here. And then I will just draw the lines from here to this point. From here to this point. And then I'm done. So you can clearly see where is the human eye. And what we are looking for is clear. This virtual image. These all are virtual lines, not real lines. So we must draw by the dotted line. And if you know the mechanism, you can really understand how to draw the ray diagram. It's not very difficult. A bit of manipulation, of course, I do, but this you can do draw this diagram logically. If you draw step by step, you can see of what is happening. And now we are done. So what is the magnification? What we are trying to achieve?
Angular magnification.
So we are trying to achieve the angular magnification. So our goal is to achieve m theta, and we know how to write m theta. It is, see, our virtual image is subtending angle theta, which is fortunately the angle subtended by the first image formed by the objective. Do you realize this? What I just said? Our final image is subtending what angle? Theta.
Theta.
And which is also the angle subtended by the virtual image. This is the virtual image h dash. Understood? So h
Yes.
dash is subtending angle theta on the eyepiece. Do you realize this? Any doubt in this, guys? If you have doubt, you can ask.
No.
So the first part is done. M theta. So we can add m theta as theta upon now. The moment I say theta naught, it is again the old definition. I cannot. The denominator has nothing to do with this diagram. The denominator is the maximum size of the object as seen by the unaided eye. That is the definition. So theta naught will follow the definition which we have already defined. Okay, so if I need to mention, theta naught is the maximum angular size of the object with unaided eye. Okay, so that definition will remain same here also. So now we are done. So how to write theta, by the way? If you look at the triangle, you can see theta we can write as h by ue, right?
Yes.
And what is theta naught? D by what?
So it is h naught by d.
Yeah, and that is h naught by d. Correct. So here the theta naught becomes So what angle subtended on the objective is the theta naught, because the light ray is coming to the objective first. So what if your eye had been at that location? You would have looking at the theta naught. So the theta naught will be how much? The unaided eye definition is same. So here the unaided angle is the angle which the objective will subtend at objective. What we can write here? D by, sorry, not D. H naught by which value? D only, no?
D only.
So we have to write H naught by D, correct?
Yes.
So theta naught is again H by UE, and then theta naught is theta is H by UE, theta naught is H by naught by D, which looks like H by H naught into D by UE. And if you look carefully, what the first term is representing? The linear magnification of the object.
Yeah.
And that is the prime goal of objective. The objective will achieve the linear magnification, and the eyepiece will do the same thing as the simple microscope was doing. It will try to achieve the angular magnification as much as possible. So this formula, the H by H naught, we can write as minus V naught by U naught. Why minus? Because you can see that the final image is inverted with respect to the first image. Compared to H naught, which is above the principal axis, the H dash is below the principal axis.
Yes.
Understood? And therefore, the answer must be negative. Although for calculation you can take it positive, but the magnification, the final magnification must be negative. So we write as minus V naught by U naught because we are writing a positive value. Okay. So the formula is V by U. V is V naught and U is minus U naught, isn't it? So for objective, the linear magnification is V by U, but V is V naught. What is U? Minus U naught, isn't it? That is why I wrote like this. Into D by U. Of course, that is the value. So we are taking D by U as value, and the overall answer should be negative because the final image is inverted with respect to the first image. Okay. And also you can think this way, that first is real, so negative answer. Second is virtual, so positive answer. Our formula is ready. Even if you forgot this answer, let's say if you have compound microscope and you just don't remember what is the answer, it is easy to remember how. How to remember this? The role of the objective is linear, eyepiece is angular, and you can recall the formula of the magnification by the simple microscope. Okay. So we can see that overall magnification the total magnification achieved by compound microscope is equals to linear magnification of objective multiplied by angular magnification of eyepiece. I hope this is clear.
Yes.
Yes.
So the m theta is okay. Now this is the formula minus V naught by U naught into D by U. And again, we talk about something called types of vision. So for normal vision or normal viewing experience, what we want the final image should be at infinity, isn't it? So the m theta, okay, when we can achieve this final image at infinity? When the UE is close to FE, isn't it?
Yes.
Do you guys realize this? That for maximum magnification, of course, it should be virtual, so it should be inside the F, but very close to F so that we can achieve the distance almost at infinity.
Yes.
Now, these are the concepts which you need to keep in mind while drawing the diagram and while solving the question. That what are the things that we can achieve and how we can achieve. So for normal vision, the UE should be on a smaller size than FE, but close to this. Lesser, why? Why lesser? Because we want virtual image. And why equal? Because we want highly magnified. So the m theta in such case will be minus v naught by u naught into d by f. And it looks like all answers are similar to the simple microscope, only with the one factor, the linear magnification factor is getting multiplied here. The rest are same. So similarly for LDDV, what we want for LDDV, and I need to go back here. In that case, this distance, carefully, from here to here, for LDDV, this should be, this is VE, and what we want is the VE should be equal to how much? For least distance of distinct vision, our VE should be equal to capital D, isn't it?
Yes.
Yeah.
So if you use the lens formula, it will give you the same answer. 1 by V. Now for eyepiece, okay, not for eyepiece, LDDV. For eyepiece, we can add 1 by V minus 1 by U equals to 1 by F. The V is minus D, the U is minus UE, the F is FE, which is plus. So 1 by UE turns out to be again 1 by FE plus 1 by D. So the final magnification we can add is minus V naught by U naught. And D by UE. So D by UE becomes 1 by FE, 1 by D. And again, you can see it is a similar answer than the before, only with one extra factor coming. And the D by F is now replaced by D by FE. So the angular magnification is achieved by the eyepiece and linear by the objective. And so the formula is quite obvious. It should not bring a lot of difficulty to understand. Is this clear, guys?
Yes.
Yes, sir.
I hope this is not very difficult. Okay. The next is so we are done with the microscope part. So we have only studied two types of microscope, I mean simple and compound. Now we are going for the distant object, the celestial world, the stars and the planets. And then comes the astronomical telescope. Okay, and then one thing I need to discuss here.
Sir.
Yeah.
What other types of microscopes are there besides the ones that we've studied?
Electron, we have electron microscope also.
Okay.
We use the magnetic lensing technique to achieve the millions times the magnification. So of course, when it comes to the study of crystals or something like this, we use the electron microscope. Also to study virus, we also use the electron microscope because the nature is all about size. So we have bacteria, fungi, virus, and so many things. And what they only differ is in the size. So let's say we have the RSPM, SPM, like suspended particulate matter. RSPM is called the respiratory suspended particulate matter, and they differ in size. So even the human body pores are big enough to allow the RSPM to enter the bloodstream, which is dangerous. Okay, so we need to know the quality of air. That is it RSPM beyond the prescribed limit, and if it is so, then it is dangerous to live there in such atmosphere. And all these objects are having different size. So to study the very small object, we need magnification in millions, and that is not achieved optically, rather it is achieved electronically, you can say. So we have the electron microscope, which uses the magnetic lensing technique, and that you will study in the chapter of magnetism. I'll give you the way it is studied, the way it is achieved. So the stream of electron is passed through the electromagnetic field, and then the stream of electron, because electrons are very small in size, they are so small that they can pass through virus also.
Oh,
So in a way, a part of virus will block it, a part of virus will let it go on the other side. So what you cast is the image of the opposite of the actual object. So we always cast the negative, then we develop the positive. I hope you know the negative and positive idea. If you don't know,
yes.
I'll tell you. Negative means we always get the complementary image. We don't get the actual image.
Yes.
So we develop the positive. So from complementary, we get the actual. That's negative and positive. Because the part of the body which is blocked by the light is casting the shadow. But what we want is not the shadow, we want the body. So that is like the idea of negative and positive. And electrons are so small that they can pass. But so they will follow the electron will follow the contour of the object, however small it may be. And you get the image of the contour from there, that is called negative, and you develop the positive. So we have, of course, we have a very powerful microscope nowadays, which can achieve billions time magnification. And that is very powerful. I mean, we need a high order of magnification to study the various types of viruses, or maybe DNA study. So DNA is again a size, it's a molecule, right? So a molecule will have some damage. And of course, you cannot see DNA using the simple microscope or compound. Okay, you need something more powerful. So in the context of JEE, Advanced and Mains, we are having very few topics to study, which are very easy to understand. Yeah, I wanted to discuss one idea, one concept, that is called the tube length. So generally, when you design this microscope, there is a tube in which these lens will slide. So generally, what we do is we fix the eyepiece, because eyepiece is the side on which you put your eye. The objective is a movable object. So objective is like a grooving. So we have the threaded groove in which you can, by turning, just like, camera, we have the rotation. You rotate and you can move back and forth. That is the whole idea. So the objective is a moving part. You can move on a thread actually. The eyepiece is a fixed part. You don't move at all. It's a fixed point from where you see. And by changing the position of objective, you achieve the maximum possible magnification. So we have something called length of the tube. That is a very famous concept. I mean, how I missed it, but no, not now. So this separation. So that technically the separation between the objective and eyepiece is called length of the tube. So these things are put in a tube. You might have seen the compound microscope, which is the pathological lab. They use the microscope. Maybe you have seen in school, or if not, you can go to any pathology lab. You can see it. All right. So okay, I'll mention here separately. So length of the tube is how much? Length of compound microscope tube It is defined as separation between objective and eyepiece. I hope this is clear. So we can write L equals to, if you look carefully, what is L? It is V naught plus UE, right?
Yes.
It is V naught plus UE. And you can define for normal vision. We have already figured out that UE is FE. And so L becomes U naught plus FE. And for LDDV, we know 1 by UE is 1 by FE plus 1 by D. So UE is actually FED by FE plus D. Okay, I hope this is clear. Shall I explain further? This I have derived already, so you can write the length of the compound microscope as V naught plus FED. So they might give you the length and they expect you to find the other unknown values. Okay. And to find V naught, you can use the length formula for objective. So if you want, you can write like this: to find V naught, use length formula for objective. This I'm leaving you as an exercise. So you all have to finish SC Verma, because the optical instrument chapter is a separate chapter in SC Verma, and solve each and every question to get the idea. Okay. So practically, now this is not what you will solve. Practically, the V naught is much bigger than UE. In fact, the first image is formed so close to eyepiece that L will take a roughly equals to V naught. The UE will have almost no value. So of course that is also there. And in such case, the magnification, the overall magnification, the practical value is minus V naught by U naught. And we keep practically we do something. So we keep U naught close to FO. We keep we assume V naught bigger than this, and we had the formula U. So practically the formula looks like minus L by F naught into D by U. Now this is the practical aspect which you are not supposed to remember. This is the aspect if nothing is given, you can go with this formula. So there will be some question based in on this formula in SC Verma. So they will give you the condition, and then you can realize that okay, what I can use and what I cannot use. So practically we try to achieve maximum magnification, maximum linear magnification. So we keep the U naught close to F naught on a bigger side because we want real answer. And L is roughly V naught because U is very small value. And the formula turns out to be this much. So this is what you need to remember. Okay. It is clear?
Yes, sir.
So the next part is called astronomical So now you want to see the distant object. So you are looking at planets, stars, and definitely it is meaningless to define theta naught in such case, because you cannot go to the at a distance capital D near the sun and you will see, oh, what's the angle. You can't see that. You will be burned out much before you reach the sun. So the idea is we don't define theta naught in context like this. Rather, we define something new. So we'll see how the size of the object refers to in case of telescope. So in astronomical telescope, we very much use a similar configuration of two lens combination. Now, because the side facing the object is the objective, and by common sense we want a very bright image of the object which are distant object. So the first thing is to increase the brightness, because the celestial body will give you anyway a small amount of light. So if you want to receive a large amount of light, the first thing is you need to increase the aperture size. So the problem with the astronomical telescope is to create as big aperture as possible. So it comes with many challenges, like a lens will create the chromatic aberration, the color will get distorted, and bigger size objects lenses always create the spherical aberration. So there are many types of aberration that the image will go through. So it is difficult to create a lens which is free from such aberration and having a bigger size. So the future was all about the reflecting telescope, in which we replace the refraction by the reflection and we achieve the same magnification. So we have Cassegrain telescope, which is the first very famous reflecting telescope. You can read more about it in NCRT or on internet. So for astronomical telescope, it is just for reading. I mean, of course, there is no question coming. And if question will come, it will be simple, the mirror formula question. So when we design the optical telescope, astronomical telescope, the first theme is to have as big aperture as possible, because the distant object will not give you sufficient energy, sufficient light, and so the image will be very dull. The only way to get the better image or bigger, I mean brighter images, to absorb more and more light, and that is only possible with bigger aperture. So bigger aperture is the first goal. Okay, we always achieve. So all the observatory in India or across the world, they use giant life-size telescopes. You might have seen in uh, YouTube or in reality. In Mumbai also we have, near Pune, I think. There is a series of radio telescope. We try to capture what the aliens are trying to say to us. So what is the first thing that we need to know is that we have a big aperture objective. Second thing is, when light ray will come from infinity or a distant object, it will come as a parallel beam of light. Come as a parallel beam. What does it mean? So we have a beam of light. We don't have one or two light. It's a beam. And we assume the beam to be paraxial. Just Okay, so let me draw some more. This is representing parallel beam of light. I'm just exaggerating this light ray. It is paraxial, but we always assume coming at some angle. The last. And we call this angle as alpha. Now, if you're looking at some star, whether the objective is looking at the star or we are looking at the star, both are same phenomena, isn't it? So the angle subtended at objective is the angle subtended on the unaided eye itself. Yes or no?
Yes.
Do you realize this? The angle subtended at unaided eye will be similar to the objective. So the angular size here we define as alpha. So the theta naught we have to replace by alpha. The first change from the finite distance magnification to infinite distance magnification in a way when the objects are not exactly finite. The next part is any parallel beam of light, if it is coming from infinity, we know after refraction, all will converge at where? At focus. So at the focus of what, which lens? Objective. So the first image is bound to form at f naught. Is this clear to everyone? Hello guys.
Yeah.
So, and the second concept is, which some of you might not be aware, that this convergence will not happen at principal axis. Why? Because my paraxial beam is slightly tilted. So paraxial does not mean it must be parallel to the principal axis. It means close to principal axis, not parallel to principal axis. The beam themselves should be parallel. How many of you are finding this difficult? It's counterintuitive, what you have studied so far. So the first image will form off the principal axis, and this is the image. Understood? So if this is alpha, so because we know the line passing through the optical center will also form alpha. So all this diagram is slightly disturbing because the way I have drawn, but let me try to compensate somewhat. I'm trying to be politically correct actually here, but nevertheless. So this angle is alpha, and this alpha is called the angular size of what? The alpha is called the angular size of object. That's simple. Angular size of object. And the location is predefined. You can easily say this is equals to f naught without any doubt. And this is the this is your, let's say if I'm looking at some star, maybe sun or moon, this is the size of the moon that you will see here. And the moon may have some diameter like this. Small. Okay. So this is the size. The next is, of course, what you want. It's similar to what we did earlier. The next thing is we want magnification. We want a bigger angle. How are we going to achieve this? How to get the bigger angle? So we need to bring another lens. Actually, which lens? Eyepiece,
I
isn't it? Now eyepiece should be closer to the object because we want what we want. We want something, right? We want one thing. We want a virtual image of the first primary object made by the objective. And therefore, I'll draw a line from the tip to this center. And I can see clearly if I do so, I will not be able to draw the line properly. So I'll make a manipulation as usual. Yes, this is better. I'll shift it here. And then I'll make one more modification, extend the line. Well, so now we got something called beta. So what beta represents? Okay, we'll see that what beta represents. So this light ray, this is the line. This is the line just for the idea. Okay, what is the angle subtended by the first object, first image on the eyepiece. This is eyepiece. The other values we need to mention here is the distance of the first image from the eyepiece, and we call it UE. Well, that's fine. And what else? Yeah, so now I'll do the extension part. So drawing the diagram is like some piece of art, which I always manipulate. Oh. Like I have very less choice. Yeah, don't worry, I can manipulate all this as per the space available on my screen. Yeah, this is better. Okay. No, this is better. Yes. All right, so we got it. Don't worry. So we always have the room to manipulate like this. So what we want is we want this light ray, the beam which is coming here. This beam after, okay, let me draw this line also. The virtual part. And what else I'll do? I will take the two extreme. So, okay, so this is coming here. Yeah, now I'm doing some artistic jugaad actually. So one more change, I need to extend the lens. And the last thing is I will join this point to the tip. Yeah, it's fine. And we'll extend this line here. Oh, gonna change. Finally, after all this hard work, we got the human eye located here. And now I have to remove the virtual object. Okay. So I hope you can see the ray diagram, which is very easy to draw only after 1000 practice. But if you know the logic, probably you can draw. So at home, you can try the ray diagram. Okay, I'm drawing not by looking at anything. I'm drawing by logic only. That's why I'm trying to manipulate things as it is coming to me. So if you can also try, you can try to draw through the logic, and eventually you understand, okay, how these diagrams, which looks really complex and intimidating, I mean, you can draw it actually. It's not difficult. So we have everything ready. The theta here becomes what? What is theta here? Theta is the angle subtended by the final image on the eyepiece.
Beta.
Beta. Right. So we got theta naught, we got beta. I mean theta and theta naught. So what is the definition of magnification? M equals to theta by theta naught, right? So technically it is beta by alpha. I hope this is clear.
Yes, sir.
Yes,
And
sir.
I'll put a minus sign without asking anyone. Why? Because if I imagine my son to be, I mean, my son means everyone's son, the sun, the god. You can see the tip has inverted, right? After reflection, the tail is somewhere here and tip is somewhere here, isn't it? So that is how we think about it. So it is the inverted image. So compared to, see, I mean, of course, in case of celestial body, it doesn't matter whether you look at the moon inverted or erect. It's moon, it's a round object. But still we can define. So what we generally do is we ignore the sign actually. In case of this, in reality, it is inverted. So let's say we have a distant planet in shape of a rod. I mean, of course, that's hypothetical only. But imagine if we have a, yeah, we can talk about the comet. Comets are like a rod, the linear object. And you're looking at a distant comet. Then the comet will appear inverted. Okay. That's what possible. Anyway, so the idea is we have the angular magnification defined as beta by alpha. And it is very easy to solve this question because the beta and alpha. So we will take only magnitude of magnification while solving question. Okay, so we just take the magnitude part. And that's one more thing I should have done here. The arrows, it looks nice. So the magnitude of magnification we can just write as m theta equals to beta by alpha. And what is the value of beta? Value wise, what you can write? Numerically,
D by U.
beta is d by ue. What is alpha? It is d by fo. And we're done. It's a, after such a huge effort in putting this diagram, the formula is like a very simple. Fo by, that's it. We are done. Such a simple formula. For astronomical telescope, the answer is f naught by fe. F naught by ue. It is clear?
Yes.
And of course, what is the next step? We have to invoke the types of vision. So for normal viewing experience, what will do? For normal vision, tell me guys what we can write. For normal vision, the UE must be FE, right? We have been doing this
Yes.
again and again. And therefore, the magnification in such case becomes FO by FE. This is the value wise. We always write value wise. So how to achieve magnification? It is only possible when FO is. So technically, we keep the focal length of objective very large. So objective is like a very close to thin and flatter surface. Okay. Eyepiece is very curved. So the FO is much bigger than FE, and therefore we achieve up to 100 times or maybe 1,000 times magnification. So we keep FO more than FE. Technically, this is more is sufficient, but in practical aspect, we keep FO much bigger than FE. And that is why we also use the large size aperture for light to enter, and also keep the focal length of objective very big actually. Now the problem is, if you keep the F1 really large, you know that the tube length will become really big, because if the light will converge after long distance, that will increase the tube length, and that will
Yes.
also decrease the convenience of viewing the object. We need to rotate a large tube mounted on some spindle to look at some star in the sky, which is the case with a large observatory. If you have seen, they have whole big dome. From the dome, the telescope comes out, and the telescope will have a very large length, up to a few meters. And you know why we need to use the big tube length? We don't have option actually. To achieve the larger magnification, the tube length has to increase, isn't it? Do you guys realize this part? The objective will have large value, so it will go farther. Yes or no?
Yes.
Yes.
Yeah.
Which will definitely increase the tube length. Yes or no?
Yes.
That is logical. So the first thing which we need to remember, that the magnification is for the normal vision is just sorry. Okay, so for normal vision, this is the answer. But the question is, what is the length of tube? For normal vision, how much big length the tube is required? F naught plus UE. I hope you remember the length definition. Once again, I'll put it here. This is the length of tube. Length of tube. And yeah, this is easy to write, right? So what is L value? F naught is fixed. I cannot change the F naught, but I have to write UE. And because we're talking about the normal vision, the UE becomes, since so in this case, the L becomes FO plus FO plus F. And perhaps this is the biggest length of the tube that we need to design. So knowing the F naught and FE, we know how big the tube should be. Okay. If F naught is really bigger than FE, then the tube length is roughly F naught. So if in the question they mentioned that the assume F naught is much bigger than FE, you can take the length of the tube exactly equals to F naught. I hope this is clear what I'm saying.
Yes.
The other part is called for LDDV, the least distance of distinct vision. So for the least distance of distinct vision, we have to use the same logic, the 1 by V minus 1 by U 1 by F. But we have to write this for apply the lens, applying, okay, let's call applying lens formula for eyepiece, right? We have to talk about eyepiece now. So what is V? What V you want? Minus D. What is U? Minus U. What is F? F. And see, it's again the same typical answer. Every time I get the same answer. It is kind of boring, huh? No, but anyway. So the UE turns out to be how much? FED by FE plus D. And therefore the length of the tube. First of all, we need to talk about the magnification. So what is the magnification? For magnification, it is f naught by UE, and this turns out to be f naught into 1 by FE plus 1 by D. This looks difficult to remember, but easy to derive. Okay. And the last thing is, in this situation, what will be the length of the tube? The length of the tube will be, tell me guys. What is the length of tube?
UE value we got.
F naught plus FE by FE plus D. Is this clear, guys? I hope this is not difficult. Clear, guys? Yes or no?
Yes.
Any doubt in this? Okay. Now the problem was this telescope is that okay, it's fine to look at the moon, star, and all because they are round shape object, and even it is inverted, it's we will not mind. But imagine someone is using this lens to watch the live match in stadium. So you buy your binocular, you go to stadium, and imagine the binocular is working on this strange arrangement of lens. Every player will look running upside down, and I think that is not so convenient to watch, isn't it?
Yeah.
Yes.
So I think none of you will favor this kind of telescope, although it's really good. But for good viewing experience in a cricket stadium or football stadium, we need to shift the image position from down to up, or you can say in the same side. Okay. And for that, what we use is called terrestrial telescope. So the next telescope is called terrestrial which is your general binoculars. So it is having the similar arrangement as before, with one extra lens come as a auxiliary lens. We call it auxiliary lens. Auxiliary lens. And that lens we put in between the objective and eyepiece to erect the first image. So what we do is simple. This auxiliary lens will be put in between, and what it will do is, if you remember the first image we formed at something like this, if you remember the first image from the objective.
Yeah.
Okay, you don't remember, huh? The first image by the objective was something like this, isn't it? So the parallel beam of light coming from the distant object. Okay. Okay, I'll do this smart. So our diagram was something like this so far, right? If you remember, alpha. So we do not want to change anything, but we just want to bring this image, the first image, on the upside. Okay. So what we do is, if I choose some auxiliary lens of focal length f, so where we should keep the object to form the same size image on the other side? What should be the separation, guys? I want to form the real image on the other side of same size.
2F.
So what we do is we put a 2f distance on this side, and what we'll get is 2f on the other side, exactly same size. So the first step is this. We simply change the size, but eyepiece will do the same job. It will form the. So now my eyepiece is somewhere where. Okay, I'll decide later on. So this is a better place for my eyepiece because I don't have much space left. Even if you want, I don't have much space. This is better. Yeah. Yeah, I think this is correct. So the angle beta, you can see the alpha was the same. This was the H or D. Now this H will be here also again H. And now the beta will come this side. The only difference is now I can see the erect image. Okay. So everything remains same. Nothing much will change. So if I want to extend everything, it's challenging. This is so difficult. And now I'm left. Okay, I don't have a space left. Uh, so you can imagine what will happen. This lens I need to extend further. It's going beyond this dimension, and eventually it will touch somewhere. Oh, sorry. And then from there I have to draw a line. Okay, this is a really bad experience for you guys. I mean, it will touch somewhere. I mean, you can't see it. Okay, so and from there it will come back here. So it's really challenging. I mean, okay, the space put me constraint. I can draw, but I have to remove everything. I hope you can understand. Okay, this is not required. What you just need to remember is nothing will change. Why nothing will change? Because the auxiliary lens is bringing how much magnification? What is the magnification achieved by this lens? 1. So it is not going to affect the total magnification. So the total magnification will be same as before. And we always write as FO by UE. So this is UE. This is F naught. So the alpha, of course, this because this is beta by alpha, and so beta by alpha, and beta is how much you can see it is H by U, and alpha is H by FO. So in short, this is FO by U, and what you can see that the lens in the middle is only affecting the side, I mean side of the final image. So it is instead of bottom, it is forming on the right side. So what you see is the erect image, which is convenient to watch to have a better viewing experience. The other thing that it will change is the length of the tube. So the length of the tube we have write is F naught plus 4F plus U. The rest of the discussion is same. So I'll write quickly. For normal vision, the L becomes base plus 4F plus FE. For LDDV, the L becomes F naught plus 4F plus FED by FE plus D. I hope this is clear to all of you. Is this clear, guys?
Yes.
Yes or no? Yeah, slightly difficult experience. I know it's difficult to read around, but generally in a whiteboard, it's difficult, but on a classroom, I should draw up anywhere on the wall also sometimes. Anyway, so the idea is how to draw is not important. What is like, what are the key concepts? What we need to remember? So you need to remember two things. One is the magnification formula. Other is the length of the tube formula. And in case of telescope, the length of the tube is really important concept. Okay. So the two types of telescope we have seen. The third type is called, and the last type, which is very easy to remember, which I will not draw at all. And that's called the Galilean telescope. So what is Galilean telescope? So it does the same job. Instead of inverted forms the erect image, and therefore it changes the nature of lens. So what I mean, Galileo did, and maybe I don't know whether it is in the honor of him or it is actually discovered by him, but I think he discovered it actually. So Galileo was working with some optician, I think. Uh, There's a story, nice story about this. This is not good. So we keep the objective always convex. Why? Because we want the real image. So first of all, because we want the first image must be real, so we cannot compromise with the objective. So objective is still going to be convex. And okay, I'll do this or this small trick. Alpha and all. And what you do next is okay. Anyway, okay, don't worry. I'll make it. So now, okay, I need to do two things. Okay. So what is happening is we want the erect image as only thing, and here we don't achieve magnification, rather it will make it smaller. So this is alpha, again it is alpha, alpha, and this is the first image, assuming if it is formed by the convex lens, the eyepiece becomes now concave, and we know the idea of concave. So this is the first image, and the first real image of objective will act as the virtual object for eyepiece. I'll write it in words. First, first real image of objective will act as virtual object for Ix. Yeah, that's it. So first real image of objective will act as a virtual object for Ix. And to represent as a virtual, I'll make it. Oh, fine. And then the same process will occur, happen again. So I have to draw something from here to the center. And anyway, so the light ray after refraction will bend away from normal. Just to confuse you. Just okay. So now this will be this. The eye is here. And now you look at the object here. And this becomes this will be the U. And the entire thing is from here to here. Again, F. So the only difference is the magnification will have now positive value, because you can see FO and UE both are positive. So earlier we forced ourselves to write as positive value, but actually the answer was negative, but now we can actually write positive value. So nothing will change. You have to write as FO by UE, the same definition. And something interesting which happens here is the length of tube. The length of tube will be FO minus UE, the value wise. If you want to confuse, not to get confused. So our length will change. So that is the only difference in the formula. The length will change. So again, you can add for normal vision. For normal vision, same logic. FO by FE, and the L will be FO minus FE over and out. And for LDDB, tell me guys, what we can write for LDDB? For LDDB, the M becomes FO into 1 by. Okay, now we have to write in value. So let me solve it. 1 by VE minus 1 by UE equals to 1 by f. Okay, let me add the formula first. V minus u. So do it for the eyepiece. Eyepiece. What is the V for the concave lens? Minus D. What is the U for the concave lens? Plus U.
U.
What is the focal length of concave lens? So for concave, we are at minus in value. So what you will get here is 1 by UE turns out to be 1 by FE minus 1 by D. It is a minus sign. And therefore, yeah, the M becomes FO into 1 by FE minus 1 by D. And the length of the tube will be how much? F not minus the value which is how much here? FE D upon.
PD up.
No, sorry. Yeah, perfect. D minus F, right? D minus F.
Yes.
All right. So the only difference is, if you remember the formula for the first case, just replace FE by minus FE, you get the same answer. Yeah. In this formula, simply substitute minus FE instead of FE. The Galilean telescope will come out of it naturally without any extra effort. The next concept is, this is the end of the optical instrument. Okay, so I'll take one lecture for doubt only, or not one lecture, it will take hardly half an hour, maybe 1 hour. So your homework is you have to finish the entire SBRMA of optical instrument. And if you're getting any doubt, which you will get for sure, you can ask me in the next lecture. And next lecture, I'm going to start wave optics. Time will be same, 3 p.m. Today is what? Monday. Today's Monday, no? Sunday.
Oh no.
This is Sunday. Okay, I don't remember. Anyway, Sunday 3 p.m. I'm going to start wave optics. You all can attend.
Okay.
And enjoy the wave optics.
Yes.
Okay. So wave optics will take at least 4 to 6 lectures. It's a big topic, and it will also cover the diffraction, and to cover the polarization, and it will cover the everything. So everything from the wave optics, polarization, and all, we are going to cover it.
That
Okay.
chapter is also for advanced.
Yes, wave optics is for advanced. Definitely.
So,
Yes.
sir, so do we have like on Tuesday?
Tuesday. Yeah, Tuesday we can keep. I mean, that's a good idea.
10 to
We had
2.
discussed yesterday only.
Yeah.
10 to
So
2.
we'll keep Tuesday also. Yeah, that's fine. I think
Okay.
no one
So,
should have the issue with Tuesday, 3 to 5 or 3 to 6. Okay. So on Tuesday also we'll start the wave optics. Right now you can take a break. Those who are having lecture from 6 o'clock can come back at 6. Bye guys, take care.
Bye, sir. Thank you, sir.
Bye, sir.
Thank you.